To prove the existence of irrational numbers, a right-angled triangle ABC was considered. The triangle was such that these two sides equaled 1, and the length of the hypotenuse was supposed to be found out. The Pythagoras theorem was used to get AC squared equals AB squared plus BC squared. AB and BC both equal 1. Substituting those values here, we got AC squared as 1 squared plus 1 squared, which equals 2. If AC squared is 2, AC will equal square root of 2. And Hippasus said that this is an irrational number. But why? How did he prove it? He used an indirect proof, and this is how he went about it. He said, let root 2 be a rational number. It implies that root 2 can be written as p by q, where p and q are integers which do not have a common factor. P by q is in its simplest form. How do we eliminate the radical now? To eliminate the root sign, we square both sides. So 2 equaled p squared by q squared. Transposing q squared to the other side, we got p squared equal to 2q squared. This gives us a very important result, and let's call it our first equation. What does this tell us? We know that 2 multiplied by anything is even. So the first equation tells us that p squared is even. It also means that p is even. That's because if the square of a number is even, the number has to be even. 2 squared is 4, 6 squared is 36. If the square is even, the number is also even. So let p be equal to 2a. An even number is always in the form 2 multiplied by something. Substituting this value of p in equation 1, we get 2a the whole squared equals 2 multiplied by q squared. A can be any constant. Opening the brackets, we get 4a squared equals 2q squared. Cancelling out the common factors, we get q squared equals 2a squared. Observe the right hand side. It's 2 multiplied by something, which means that q squared is also even, which means that q is also even. Wait, this gives us an interesting result. It tells us that p and q are both even numbers. This simply means that 2 is a common factor of p and q. If both are even, they will surely have 2 as their common factor. But look at what we assumed. We assumed that p and q have no common factors. So this is a contradiction to our hypothesis. Hence, root 2 is not rational, and numbers which are not rational are called irrational numbers. We can say that root 2 is an irrational number and cannot be expressed as p by q.